2. 1 2 1 2. At the backbone of every program or piece of software are two entities, data and algorithms. Java, Python lists and dictionaries, JavaScript. 1, 2. Well, I forgot that this was up. And I'm trying to get through this right now. I'm not gonna lie. In this moment, it feels difficult, but I'm gonna make it work. So, I was going through the more extrapolated data structures and algorithms course in Codecademy, but I realized that I need to be efficient with my time, and it seems like this course, which is more pertaining to passing the technical interview, will allow me to be more efficient with my time. So you just saw me kind of understand what the differences between the two courses are and zoom past the stuff that I already covered in the last video or the last two, I think, where I did linked lists and doubly linked lists in the other course. And it seems like I went into much deeper depth in those courses than I would have in this one, which is good. But now I'm into the search part of the syllabus for this past the technical interview course. So I don't, information doesn't really sink into my brain unless I read it out loud. So I will now proceed to read this out loud. Linear search. Imagine that you are a DJ at a party. The diagram on the right shows your playlist for the event. A party guest wants to know if Uptown Funk by Bruno Mars is a song on your playlist. You would scan the entire playlist and find that it is not on your playlist. Another party guest wants to know if Single Ladies by Beyonce is a song on your playlist. You would scan the list until you locate Single Ladies as the 5th song on your playlist. With this information, you could inform the party guest that the song is on the playlist and that it will be the 5th song that it will be played. In computer science, search algorithms are step-by-step procedures used to locate and retrieve information from a set of data. This method in the example is similar to a search algorithm called linear search. The linear search or sequential search algorithm sequentially checks whether a given value is an element of a specified list by scanning the elements of a list one by one. It checks every item in the list in order from the beginning to end until it finds a target value. If it finds the target value in the list, the linear search algorithm stops and returns the position in the list corresponding to the target value. If it does not find the value, the linear search algorithm returns a message stating that the target value is not in the list. How many songs would you need to check in order to find Kimbara by Celia Cruz? 1, 2, 3, 4, 5, 6. Finding elements in lists. Linear search can be used to search for a desired value in a list. It achieves this by examining each of the elements and comparing it with the search element, starting with the first element to the last element in the list until it finds a match. The steps are: 1. Examine the first element of the list. 2. If the first element is equal to the target value, stop. 3. If the first element is not equal to the target value, check the next element in the list. 4. Continue steps 1 to 3 until the element is found or the end of the list is reached. For example, we can use the linear search algorithm to find the target value 22 in a list. The algorithm iteratively moves through the list until it finds the 22 in the 7th position of the list. Instructions: use linear search to find 23 in the list of numbers on the right. It appears twice. Would linear search stop when it reaches the 3rd element or the 9th element of the list? So it would stop when it reaches the 3rd element. Best case performance. Linear search is not considered the most efficient search algorithm, especially for lists of large magnitudes. However, linear search is a great choice if you expect to find the target value at the beginning of the list or if you have a small list. The best case performance for linear search occurs when the target value exists in the list and is in the first position of the list. In this case, the linear search algorithm will only be required to make one comparison. The time complexity for linear search in its best case is O of 1. You decide to visit a new coffee shop for an espresso. Unfamiliar with their menu, you are unsure if they serve espresso, so you use linear search to scan the menu. You are able to efficiently find your desired drink because it was at the top of the menu. How many comparisons were made to find espresso on the drink menu? 1. Worst case performance. There are 2 worst cases for linear search. Case 1, when the target value is at the end of the list. Case 2, when the target value does not exist in the list. In both cases, the linear search algorithm is required to scan the entire list of n elements and, therefore, makes n comparisons. For this reason, the time complexity for linear search in its worst case is O of n. In one of the worst cases, the target value is found. Is this case more efficient than the second case because it was able to find the target value in the list? Leave your thoughts on this post in the forum and then click next. Average case performance. If this search was used 1,000 times on 1,000 different lists, some of them would be the best case, some the worst for most searches. It would be somewhere in between. On average, it would be in the middle of the list. That search would take O of n over 2 time. Let's prove this. Each element of the list on the right requires a different number of comparisons to be located in a list. Using linear search, the first element is located with 1 comparison. The second element is located with 2 comparisons, and so on until the last element is located in n. The size of the list comparisons. The average case performance is the average number of comparisons. To calculate this, you use the formula sum of number of comparisons for each element, number of elements in the list. We won't show the math, but we can simplify things by reducing the equation to n over 2. We would expect on average for the linear search algorithm to search halfway through the list. Therefore, the time complexity for linear search in its average case is O of n over 2. Based on Big O simplification rules, which you can learn about in the Big O lesson, we simplify the time complexity in this case to O of n. How would you calculate the average case performance of the list on the right? So there's 7 elements, so it would be O of 7 over 2. Time complexity of linear search. Linear search runs in linear time. Its efficiency can be expressed as a linear function, with the number of comparisons to find a target increasing linearly as the size of the list n increases. The time complexity for linear search in Big O notation is O of n. The time complexity of O of n means the number of comparisons is proportional to the number of elements n in the list. With a list with twice as many elements, linear search will take at most twice as long to perform the search. The time complexity of linear search is also dependent on the best case, worst case, and average case scenarios. What is an example where linear search would be a good choice to search for values? What is an example where linear search would be a bad choice to search for values? Good, short list, it's up first. Bad choice, long list. Review. Congratulations. You've learned how linear search works and how to use it to search for values in lists. Let's review what we learned. Linear search is a search algorithm that sequentially checks whether a given value is an element of a specified list by scanning the elements of a list one by one until it finds the target value. The time complexity for linear search, O of n, is O of n, but its performance is dependent on its input. Best case, the algorithm requires only 1 comparison to find the target value in the first position of the list. Worst case, the algorithm requires only n comparison to find the target value in the last position of the list or does not exist in the list. Average case, the algorithm makes n over 2 comparisons. Linear search is a good choice for a search algorithm when you expect the target value to be positioned near the beginning of the list. A search needs to be performed on an unsorted list because linear search traverses the entire list from beginning to end, regardless of its order. So again, linear search is a good choice for a search algorithm when you expect the target value to be positioned near the beginning of the list, or a search needs to be performed on an unsorted list because linear search traverses the entire list from beginning to end, regardless of its order. Learn binary search. With a sorted data set, we can take advantage of the ordering to perform a search which is more efficient than going element by element. Let's say you were looking up the word telescope in the dictionary. You wouldn't flip through the A words and B words page by page. Alright, I understand the basics. I kind of want to see this stuff implemented though. Time complexity of binary search. This is good to think about. How efficient is binary search? In each iteration, we are cutting the list in half. The time complexity is O log n. A sorted list of 64 elements will take at most log base 2, 64 equals 6 comparisons. In the worst case, comparison 1, we look at the middle of all 64 elements. Comparison 2, if the middle is not equal to our search value, we would look at 32 elements. Comparison 3, if the new middle is not equal to our search value, we would look at 16 elements. Comparison 4, if the new middle is not equal to our search value, we would look at 8 elements. Comparison 5, if the new middle is not equal to our search value, we would look at 4 elements. Comparison 6, if the new middle is not equal to our search value, we would look at 2 elements. When there's 2 elements, the search value is either one or the other, and thus there is at most 6 comparisons in a sorted list of size 64. A sorted dataset speeds up searching by a significant amount. Without any knowledge about the ordering, we would resort to a linear search, taking O of n time. We would resort to a linear search, taking O of n time. What is the maximum number of comparisons that the binary search algorithm will make when searching for a value in a sorted 1000 element list? Log 1000. Correct. The maximum number of comparisons that binary search can make is log n comparisons. Therefore, for a 1000 element list, binary search will make a maximum of log 1000 comparisons. Which of the following lists of numbers would binary search not perform correctly? So, ten, 20, 35, it would not perform this one. It's not sorted. Given the following list of names, Emily, Ian, Hillary, and so on, which search algorithm would locate the name Ian the fastest? Linear search. Given the list of numbers, how many comparisons would linear search perform to locate a target value of 89 in the list? 2, 4, 6, 8, 10. Linear search is will perform 10. You are throwing a birthday party at a private venue. In order to be granted entry into the party, the receptionist at the venue must verify if the guest name is listed on your personalized party guest list. One of your party guests, Nick, is very impatient. If the receptionist uses linear search to search for names on the party list, where should Nick's name be listed so that he's granted entry into the party at the fastest rate? First on the list. I would say do not invite Nick to the party, but we'll go first on the list. Blank checks whether a given value is an element of a specified list by scanning the elements. Yep, this linear search. What is the time complexity of linear search? So the linear search algorithm checks whether a value is an element in a list by scanning the elements of a list one by one. The algorithm's iterative approach to finding a target value is useful in solving numerous search problems with unsorted data. In this lesson, you will learn how to implement the linear search algorithm as a function and use it to solve search problems in Python. Implement linear search. Linear search is used to search for a target value in a list. We examine each of the elements in the list and compare them with the target value until matching the target. If a match is found, the linear search function will return the index of the matching element. Otherwise, the function will raise a value error, a special error to indicate that the value was not found. Here is the pseudocode for linear search as a function. For each element in the search list, if element equal target value, then return its index. If element is not found, then raise a value error. Let's convert the pseudocode into Python. Declare a function called linear search in Python with 2 parameters. So def linear search with the parameters search list and target value. For now, in the body of your function, linear search, use the pass keyword. Remove pass. Create a for loop that iterates over the list using the range and len methods. So for I in range length of search list, use the iterating variable to print each element in search list. What'd I do wrong? Name values is not defined. Oh. Within the for loop, after printing the element, use an if statement that checks whether the element matches target value. If so, return the index. If we complete the loop and there is not a match, use value error to raise an exception. Add a line outside the loop, invoking raise value error with, so, oh, okay. Yeah, that's where it should go, not there, right there. Raise value error with target value not in list. I kind of forget raise value error with f target value not in list. Raise value error. Oh, okay, that's how you do it. What is it again? The format target value. Raise error. Using linear search. In the text editor, you will find the code for the linear search function that we implemented in Python. When called, our function returns either an index of an element that matches the target value or a value error. Express that the value was not found. The text editor includes the code for the linear search function, a list of numbers called numberList, and a variable called targetNumber, which stores target value that we will be searching for in numberList. Let's practice calling linear search and explore the return values for different calls to the function. We're searching for 33. Call linear search to find whether the target number is in numberList and set this to the variable result, then print result. So try linear search, numberList, target number. Call it, print result. I'll set it to a variable result. We won't always find what we're looking for within the try block provided. Search for 100 to see what happens when a value is not found in the list. finding duplicates. With a few changes to our code, we can modify linear search to solve more complex search problems. Our linear search function, linear search, currently finds whether one given value exists in a list, returns the index of the first occurrence of the value in the list, and stops. But what if we wanted to find every occurrence of the target value in a list? The following is a list of locations for your favorite music artist's upcoming tour. You want to know during which tour stops will your favorite artist be in New York City. Using the linear search algorithm, you can find that New York City will be the first stop on their tour, but the algorithm will indicate that your favorite artist will return to NYC later in the tour. In order to find all duplicates of a target value in a list, we modify the algorithm to match the following pseudocode. For each element in search list, if element equal to target value, then add its index to a list of occurrences. If the list of occurrences is empty, raise value error. Otherwise, return the list occurrences. Let's implement this in Python. Run the code to see the results of searching for target city, New York City, in tour locations. The algorithm stops and returns the first match. To find all matches, we need to traverse the entire list and save every matching occurrence. Modify linear search so that the first line within the function body is a variable declaration of matches set to an empty list. Replace the code returning the index, return IDX. Instead, add the index to matches. Rewrite the code after the for loop so it uses a conditional. If there are elements within matches, return matches. Else, raise value error. Finding the maximum value. The largest value of a sorted list conveniently is the last element of a list. The largest value of an unsorted list, however, is not guaranteed to be the last element. Imagine that you are a teacher who wants to know the highest score your students scored on a test. Consider the following unsorted list of test scores. Test scores equals 88, 93, and so on. 100 is the highest score on the list, but it is the fourth element of the list. In order to find the highest score, we must sequentially scan the entire list for the largest value. Keep track of the largest value that we have seen to date. Using test scores, we would keep track of the high score as follows. In the first iteration, 88 is the highest test score. In the second iteration, 93 is the highest test score because it is greater than 88. In the third iteration, 93 is the highest score because it is greater than 75. In the fourth iteration, 100 is the highest score because it is greater than 93. This continues until you reach the end of the list. In order to find the largest value in a list, we modify the algorithm to match the following pseudocode. Create a variable called maxValueIndex. Set maxValueIndex to the index of the first element of the search list. For each element in the search list, if element is greater than the element at maxValueIndex, set maxValueIndex equal to the index of the element. Return maxValueIndex. Let's implement this in Python. We do not need to provide a target value to the function because we're looking for the largest value. Change the function declaration of linear search to one parameter search list. On the first line within linear search, create a variable maximum score index with a value of none. As we iterate through the list, we want to check whether each element is greater than the element at maximum score index. Change the condition of the if statement if maximum score index is none, or if the element of search list is greater than the element at the maximum score index of search list. In either of the two conditions, update maximum score index to the index of the current element. Currently, the linear search function raises a value error after iterating through the list. Remove that line and return maximum score index. So So we'll remove this line first. Going about it a little backwards, that's okay. So I'm just gonna get rid of this. So if maximum score index is none, or what was it? If the element of search list is greater, or search list index is greater than maximum score index, so if those are the case, then maximum score index equals IDX. And when it's all said and done, we want to return maximum score index. Review. You are a linear search whiz. You've implemented linear search as a function in Python and used it to find a target value, duplicates, and the largest value in different search lists. Let's review what we learned. Linear search is a search algorithm that sequentially checks whether a given value is an element of a specified list by scanning the elements of a list one by one until it finds the target value. Starting with linear search as a subroutine in your code is a useful foundation for constructing algorithms to solve more advanced search problems, such as finding duplicates, sequentially search the list for all occurrences of the target value, finding the maximum value, sequentially scan the list for the largest value, and track the largest value seen to date. The linear search function is provided in the text editor. Test on your own examples. Recursive binary search. Base case. Binary search is an efficient algorithm for finding values in a sorted data set. Let's implement this algorithm in Python. Here's a recap of the algorithm. Check the middle value of the data set. If this value matches our target, we return the target value index. If the middle value is greater than our target, begin at step 1 using the left half of the list. If the middle value is less than our target, begin at step 1 using the right half of the list. As an added challenge, we are going to use a recursive approach. When using recursion, we always want to think of the problem in two ways, the best case and the recursive step. We have two base cases for this algorithm. We found the value and return its index. We didn't find the value because the list is empty. In order to reach the base case of an empty list, we'll need to remove an element at each recursive call. Define binary search, which has two parameters, sorted list and target. Binary search, sorted list, target. Our first base case is when the sorted list is empty. Within binary search, use conditional to check whether the list is empty. So if sorted list is none, value. So I guess, can I do a not sorted list? Yeah. We'll set up our recursive step, declare two variables, mid IDX and mid val. Mid IDX should be the middle index of the sorted list. So mid-val is the value located in the sorted list at the mid-index. Return these two variables like so. Return mid-IDX, mid-val. Name mid-IX. This indices must be integers or slices, not float. Recursive binary search base case 2. We now have a base case for when we do not find the value in our sorted list, but we need a base case for when we do find the value. At this step, we have three options. Base case, mid-val reaches our target. Recursive step, mid-val is less than our target. Recursive step, mid-val is more than our target. We'll tackle the alternate base case first. Let's complete the base case for when we have found the value. After the declarations for mid-val and mid-IDX, write a conditional that checks if mid-val is our target. If it is, return mid-IDX. With both of our base cases covered, we'll turn our attention to the recursive step. We have two options depending on the comparison of mid-val to target. You'll recall that our data set is sorted. We'll leverage that knowledge in our recursive step to cut the problem in half at each step. If the mid-val is greater than our target, we know we can disregard every element at an index greater than mid-IDX. Below our check for whether mid-val is equal to target, make a new conditional, check whether the mid-value is greater than the target. If it is, so first of all, if make a variable left half, that is every element in sorted list up to but not including mid-val. Return a recursive call to binary search, given left half and target as arguments. Make another conditional below the last, checking if mid-val is less than our target. Make another conditional below the last, checking mid-val is less than our target. If it is, make a variable right half, that is every element in sorted list after mid-val. Make a variable result and assign it to a recursive call to binary search, given right half and target. Why are we storing this in a variable? We're making a smaller copy of the sorted list at each recursive call, so our indices for the same values change. So sorted list 7, 8, 9, 10, 11, right half 10, 11, index of 11 in sorted list is 4, index of 11 in right half is 1. We can account for the missing indices by returning the result plus the index segments of the list we've discarded. We'll do this in the form of mid-IDX plus 1. So sorted list 7 through 11, binary search of sorted list 11, mid-IDX equals 2. 9 is less than 11. We search in right half. Within the recursive call, right half 10, 11, mid IDX equals 1. Target match, we return 1. Within original call, result is 1. Result plus mid IDX plus 1 is equal to 4. Return result plus the missing indices. Makes sense. When we search in the right half of the list and find the value, this works. Unfortunately, there's an error if we can't locate the value. We'll try to add value not found to mid IDX plus 1, resulting in a type error. Add in a conditional. If result is value not found, then return result. Otherwise, return the index arithmetic as before. Recursive binary search, review and refactor. Congratulations, you implemented a version of the binary search algorithm using recursion. Let's recap how we solved this problem. We know our inputs will be sorted, which helps us make assertions about where to search for values. We divide the list in half and compare our target value with the middle element. If they match, we return the index. If they don't match, we begin again at the first step with the appropriate half of the original list. When the list is empty, the target is not found. Our original solution solved the problem of reducing the sorted input list by making a smaller copy of the list. This is wasteful. At each recursive call, we're copying n over 2 elements, where n is the length of the sorted list. We can do better by using pointers instead of copying the list. Pointers are indices stored in a variable that mark the beginning and end of a list. Vehicles, car, jet, camel, boat. Start of list equals 0. End of list equals the length of vehicles. Vehicles, start of list to end of list. Middle of list equals length of vehicles divided by 2. Vehicles, start of list to middle of list is car and jet. Vehicles, middle of list to end of list is camel and boat. This example copies the list to show what portion is covered. We won't need to copy in the algorithm. With pointers, we'll track which sublist we're searching within the original input, and there's no need for copying. Our overall strategy is the same, but we'll need to change the following sections. Binary search has 2 parameters. It should have 4. Our base case checks for an empty list. It should check whether the pointers indicate an empty sublist. Our recursive calls use copied sublists. They should update the pointers to indicate which portion of the list we're searching. Our right half recursive calls do the same. Our right half recursive calls do some arithmetic. That's no longer necessary. Run the new version of binary search, which uses pointers instead of copying lists. So def binary search, sorted list, left pointer, right pointer, target. This condition indicates we've reached an empty sublist. If left pointer is greater than or equal to right pointer, return value not found. We calculate the middle index from the pointers now. Mid IDX equals left pointer plus right pointer divided by 2. Mid val equals sorted list, mid IDX. If mid val is equal to target, return mid IDX. If mid val is greater than target, we reduce the sublist by passing in a new right pointer. Return binary search, sorted list, left pointer, mid IDX, target. If mid val is less than target, we reduce the sublist by passing in a new left pointer. Return binary search, sorted list, mid IDX plus 1, right pointer, target. Values are these numbers. Start of values is 0, end of values is the length of values, and the result is binary search values, start of values, end of values, 288. Print element this is located at index this, dot format 288 result. And we get element 288 is located at index 4. Iterative binary search. Anything recursive can be written iteratively. As a final exercise, we'll implement the binary search algorithm using iteration. Our strategy remains largely the same as the recursive approach, which used pointers. Instead of recursive calls, we'll substitute a while loop. Give me uno segundo, 1 second. So as a final exercise, we'll implement the binary search algorithm using iteration. Our strategy remains largely the same as the recursive approach, which used pointers. Instead of recursive calls, we'll substitute a while loop. Complete the binary search skeleton. You'll need to fill in the condition for the while loop, calculate the middle index using pointers, set the left pointer when appropriate, set the right pointer when appropriate. So we have this def binary search, which takes in a sorted list and a target. Left pointer equals 0, right pointer equals the length of the sorted list. Fill in the condition for the while loop. While something, calculate the middle index using the 2 pointers. Mid IDX equals something. Mid val equals sorted list, mid IDX. If mid val is equal to target, return mid IDX. If target is less than mid val, set the right pointer to the appropriate value. Right pointer equals something. If target is greater than mid val, set the left pointer to the appropriate value. Left pointer equals something. Return value not in list. So we take in a sorted list and a target. Left pointer is equal to 0. Right pointer is equal to length of sorted list. While I guess while something's in the sorted list, right? So while sorted list, calculate the middle index using the 2 pointers. Mid index equals left pointer plus right pointer. Wrap it in parentheses. Spell it right. Divided by 2 with integer division. If mid val is equal to target, return mid IDX. If target is less than mid val, set the right pointer to the appropriate value. Right pointer. My intuition is to just do mid IDX minus 1. If target is greater than mid val, left pointer is mid IDX plus 1. List index out of range. I tried to do mid val sorted list. I knew that was wrong. So if the target is less than mid val, then the right pointer is the right pointer is, where am I? Right here. Length of sorted list up to mid IDX. And the right pointer, the left pointer is mid IDX plus 1. No. Is it length of sorted list object of type int has no length. It's an infinite loop. What am I missing? That's what I thought. Oh, right pointer. It's just mid.ex. Oh, I see. Because eventually they will either cross or become equal. But for the entire, iterative process, while we're going through the list, the left pointer should be less than the right pointer. You are provided with the code for a modified version of linear search, which sequentially searches for the maximum value in a list of numbers. If we pass this list of numbers 3, 14, 9, 22, 10, 23, 8, 50 to the function, what would be the value of maximum score index on the end of the algorithm's fourth iteration? Def linear search list, maximum score index equals 0. So again, you're provided with the code for a modified version of linear search, which sequentially searches for the maximum value in a list of numbers. If we pass this list of numbers, 3, 14, 9, 22, 10, 23, 8, 50, to the function, what would be the value of maximum score index on the end of the algorithm's fourth iteration? So the value of maximum score index on its fourth iteration would be 3. The recursive form of binary search ends when it reaches a base case. Pick the base cases for binary search. Binary search ends when the middle value is equal to the search. Binary search ends when the value of the element at the middle index is not equal to the search value. Binary search ends when the list is empty or the target value is in the middle of the list. That's the correct answer. The following piece of code performs binary search something iteratively or recursively. This one has a while loop. It's doing it iteratively. Correct. This function performs binary search iteratively, using a loop to perform the algorithm on each half subset until a condition is met, rather than call itself. Consider the given code. What will be returned by the function call linear search, numbers list 23. Def linear search list, target value for I in range length of search list. If search list I is equal to target value, return I. Return -1. Number list equals 1, 10, 23, 94, 23, 67. Linear search number list 23. And again, what's it asking me? Consider the given code. What will be returned by the function call linear search number list 23? So 0, 1, 2. Correct. Linear search returns the index of the first instance of a matching element and then stops. What does it mean if linear search returns -1? In this case, it would mean that the item was not in the list, target was not found, the end of the list, value not found. The function will return -1, a special index to indicate that the value was not found. True or false, even with the linear search algorithm implemented in a program as a function, the entire function will need to be re-implemented each time we want to perform linear search in the program. Even with the linear search algorithm implemented in a program as a function, the entire function will need to be re-implemented each time. I don't think so. Yes, with a linear search is the function that can be used repeatedly without having to be rewritten each time it is needed. When implementing binary search using recursion, you recurse on the list by changing the left and right pointers after comparing the search value to the middle pointer. When performing binary search on the list 10, 11, 12, 13, 14, 15, 16, the left pointer would be assigned to the leftmost index 0, and the right pointer would be assigned to the rightmost index 6. Given that the search value is less than the value at the middle index 13, what index value would be assigned to the left pointer? What index value should we assign to the left pointer if the search value is less than the value of the middle index? So again, when implementing binary search using recursion, you recurse on the list by changing the left and right pointers after comparing the search value to the middle pointer. When performing binary search on the list, the left pointer would be assigned to the leftmost index 0, and the right pointer would be assigned to the rightmost index 6. Given that the search value is less than the value at the middle index 13, what index would be assigned to the left pointer? Zero. It remains the same. What index value should be assigned to the left pointer if search value is less than the value at the middle index during an iteration? You are given the code for the linear search function in Python. The condition of the if statements should be filled with which of the following conditional statements? Def linear search, search list, target value for I in range length of search list. If search list I is equal to target value. You are given the code for the duplicate search function, which searches for duplicates of the past target value in search list. What does this function return if there are matches? Returns an array. So returns an array of indices of all occurrences of target value in search list. Nice. Searchcademy. In order to test a product, many companies use empty or fake data. Our company Searchcademy uses empty, sparsely sorted data to test its awesome search engine. What exactly does that mean? Sparsely sorted data is data such that there is empty data in between the sorted values. For instance, an example data set might look like this. In this project, we will implement a modified version of iterative binary search to search through a sparsely sorted data set. If you get stuck during this project or would like to see an experienced developer work through it, click Get Unstuck to see a project walkthrough video. Set up the function. Within the function, sparse search after the print statements, do the following. Oh wait, did I? Wait, hold on. Okay, start yet. So within the function sparse search, after the print statements, do the following. Create two variables, first and last, and set them equal to the first and last positions in the data set. Oh, positions. Next, we will keep iterating until we find our search value. Create a while loop that checks if first is less than or equal to last. Check if the middle is empty. Within the while loop, create a variable called mid. Set it to the average of first and last. Sorry, the average. Goodness. Yep. Now we will check if the middle is empty. If so, we will search surrounding values. In the while loop, create an if statement that checks the following. if mid of the data is empty. So if data mid equal to an empty string, now we will check the surrounding values. Within the if statement, do the following. Create a variable left and set equal to the position directly left of the mid. Create a variable right and set equal to the position directly right of mid. Still. Within the if statement, create a while loop. Create a while true loop. In this loop, we will be checking if the surrounding values are empty and will break once we find a non-empty value. First, we will check if we have iterated through the entire data set and have not found an empty value. In the new inner while loop, check if both of the following conditions are met. If left is less than first and right is greater than last. So do the following. Print either use fstring or string.format. format. Now we will check the value to the right in the inner while loop. Create an elif statement that checks if both of the following are true. Right is the less than or equal to last. The inner while loop check. Create an elif statement that checks if both of the following are true. Right is less than or equal to last. Data right is not empty. So do the following: submit equal to right. Break out of the inner while loop. Now we will check the value to the left in the inner while loop. Create another elif statement that checks if both of the following are true. If so, do the following: set mid equal to left. Break out. If none of the statements are true, then we will move our pointers in the inner while loop. After the conditional statements, do the following: increment right by 1, decrement left by 1. Check if the search value is equal to the middle. Now that we handled the empty data, let's continue with regular binary search. We will first check if the middle of the data is equal to our search value. Outside the inner while loop and below its encompassing if statement, check if the following is true. Mid of the data is equal to the search val. If so, do the following: print the statement. So this corresponds to the search val, and 1 corresponds to the mid. Return from the function. I'll be honest, the empty data. Let's continue with regular binary search. We'll first check if the middle of the data is equal to our search value. Outside the inner while loop and below its encompassing if statement, check if the following is true. Mid of the data is equal to the search val. If so, do the following. below the if statement, check if the following is true. Search file. What happened? Suppose that it isn't working on. Hmm. You know, part of me does wonder why, but also I recognize that I wasn't paying full attention. I'm not feeling well. I gotta admit that. I'm gonna go ahead and hit next, and now it's moving on to cues, but I'm gonna go ahead and, at least for right now,